So this session we're going to continue on from where we left off with probability. So in the last recording we finished off doing a tree diagram, if you remember, and the branches. Hope everything went okay with that one. That is now leading me on to what is called the binomial distribution, or more commonly known in your textbooks as Bernoulli Trials. A question that comes up in the Leaving Cert asks you whether an event is an example of a Bernoulli trial. So Bernoulli trial is a special case experiment, and it satisfies these four conditions. Its fixed number of trials, which we call n. So Bernoulli trial has a fixed number of trials. It only has two possible outcomes in each trial, success or failure. The trials are independent, and the probability of a success in each trial is constant. So let me give you some examples of Bernoulli trials. Flipping a coin, an unbiased coin, that is an example of a Bernoulli trial. Perhaps I'm going to flip it 10 times. So that is a repeated number of trials, only two possible outcomes, success or failure. So success is whichever one I would like to see on my coin. Maybe I've chosen heads. So in that case, heads is success, tails is failure. The trials are independent. The outcome of one flip of the coin does not in any way influence the outcome of the second flip of the coin. And the probability of a success in each trial is constant. So in this case, flipping a coin, the probability of success is 0.5. Okay, another example of a Bernoulli trial is throwing a dice and getting a 6. So perhaps we're playing a game, perhaps we're playing Monopoly, and you need a 6 to get started, perhaps. Or Ludo, one of those ones you need 6 to get started. A fixed number of repeated trials, yes, we're going to throw it for the duration of the game. There's only two possible outcomes in each trial, success or failure. Now watch this one, because throwing a 6 is a success. Throwing any of the other 5 numbers is a failure. So even though there's 6 outcomes from a dice, there's only one success, which is 6, and all the rest are failures. So that is a Bernoulli trial, in that you can have an event which is a success and an event which is a failure. The failure being any of the other 5 numbers. The trials are independent. Throwing a 6 does not influence whether I throw a 6 on the next throw, and the probability of success is the same. Yes, the probability of throwing a 6 is 1 over 6. So Bernoulli trials, very important. There's a formula for a Bernoulli trial. The probability of having a set number of successes, which we donate over, is n choose over the probability of success to the power of or the probability of failure to the power of n minus or. Okay, and I think probably the easiest way of doing this is to do an example. Okay, so let me just get my pen and read example 1. So 5 unbiased coins are tossed. Find the probability of getting 3 heads and 2 tails. Okay, and then part 2 asks me the 5 coins are tossed 8 times. Find the probability of getting 3 heads and 2 tails. So 3 heads and 2 tails exactly 4 times. Give your answer correct to 3 decimal places. Okay, so let me share my screen with you now. Okay, so the probability of getting 3 heads and 2 tails. Okay, so I'm going to do it without Bernoulli's trial formula and then with the formula. Okay, so the probability of throwing 3 heads and 2 tails, well, you're tossing a coin 5 times. So I could get a head, a head, a head, a tail, or I could get a head, a head, a tail, tail, a head, 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 tail, head, tail, head, tail, tail, head, head, and so on and so forth. Okay, and work out the probability of each of these. So the probability of a head by a head by a head by a tail and by a tail. So go back to the last recording, I need a head and a head and a head and a tail and a tail. So that's why all of these probabilities are multiplied by each other. Or, and that's why I'm plussing, I'm happy with a head, a head, a tail, a head, work that out. Or I would be happy with a head, a head, a tail, a head, a tail, and so on all the way down. Okay, so you work out each individual line and then you add all the probabilities together. All of the different combinations of doing 3 heads and 2 tails. Okay, so this is where the Bernoulli trial formula comes into its own, because it's much shorter than obviously working all of them out. So the formula is N choose or probability of success, probability of failure. Okay, so this is the formula for Bernoulli trial. Okay, now what do all of those letters mean? Okay, well, N is your number of trials. So out of the 5 trials, I'm going to say my success is a head. So that's my probability of success. My failure is tails. My number of trials is 5. And how many successes do I want? I want 3. Okay, so that's all the letters down the side, and that's the formula. You won't be too surprised to know that I don't really go by the formula. I do use it, but it's more of a story that I tell to help myself remember it. So what I say is, out of the 5 trials, I would like 3 heads. Okay, I have deemed that heads is successful. The probability of getting a head is a half, and I would like 3 of them. The probability of getting a failure is also a half, and I would like 2 of them. So these are my 3 heads. These are my 2 tails. And this is the number of ways I can get 3 heads and 2 tails. Okay, so just to tie that into what we were doing above, in all of these lines you will see there's my 3 heads, which is this 3 here, and these are my 2 tails. Okay, now I know the probability is the same in this particular example, but they're not always the same, okay, but the method works the same regardless. If I take a different combination, so there's my head, and my 3rd head over here, so that's this half to the power of 3. This is my tail, these are my tails to the power of 2, okay, because a half by half is a half squared. Okay, and then this 5 choose 3 down here is the number of combinations of 3 heads and 2 tails that can occur. So 5 choose 3. Okay, let me just put that into my calculator. And I am getting, for this one, 5 over 16. Okay, Now, a good question may be, how did I know that heads were successes? Well, actually it doesn't matter what you deem as a success. In many cases the question will tell you, but as long as you match it up, it shouldn't matter. So, let's just say you thought heads. We follow the same format. Let's just say we thought that our success was tails. So that became my P. We thought that our failure was heads. That was Q. We're still doing 5 trials, except in this case our R is 2 because we want our number of successes, which we're deeming to be tails, to be 2. So to set up my Bernoulli trial then, out of the 5 events, I would like 2 successes. So I want 2 tails. And this is only because you have chosen tails to be your success. Okay, my probability of success, probability of tails is 1/2, and I'd like 2 of them. My probability of heads is also 1/2, and I would like 3 of them. So this is my 3 heads in this case. This is my 2 tails in this case, and this is the number of combinations. Okay, so 5 choose 2. So let me just put that into my calculator. And not surprisingly, I also get 5/16. Okay, so when it doesn't say which is success and failure, you choose. But you have to be careful that you match your R value to whatever you decide your success is, and that you choose the right probability here for success. Okay, so that's part 1 of the question, 5/16. Now, you tossed all 5 coins 8 times. What's the probability of getting 3 heads and 2 tails exactly 4 times? Okay, so I would say to you, what is the probability of getting 3 heads and 2 tails exactly once? Well, it's 5/16. So therefore then, out of the 8 times that I do this event, I want exactly 4. Exactly 4 times. The probability of getting 3 heads and 2 tails is 5/16, and I want that to happen 4 times. Okay, so therefore the probability of it not happening is 1 minus 5/16, which is 11/16. So the probability of failure is 11/16, and I also need that to happen 4 times. So small things you should notice. This number here, this R, will always match here. The other thing you should notice is that this number and this number must equal this number. Okay, because that is the number of times that you are doing the event. This is your successes, this is your failures. Okay, so if you're going to do an event 8 times, then the number of success plus the number of failures must actually equal the number of times you do the event. Okay, let me put that into my calculator. 8 choose 4 by 5/16 to the power of 4 multiply by 11/16 to the power of 4. And for that I am getting 0.14913, 3 decimal places, 0.149. Okay. So I hope that makes sense. So it does take a bit of practice to get into this. I'm going to have a look at example 3 next. During a match, John takes a number of penalty shots. The shots are independent of each other, and they have to be. That's for a Bernoulli trial. And his probability of scoring with each shot is 4/5, which also means that his probability of not scoring is 1/5. Find the probability that John misses each of his first 4 penalty shots. Okay, again, let me just take down this. John takes, the shots are independent, so the probability of scoring is 4 over 5. Therefore, the probability of not scoring is 1 over 5. Okay, so part 1, John misses each of his first 4 shots. Part 2, find the probability that John scores exactly 3 of his first 4 shots. Part 3, if John takes 10 shots, find the probability that he scores is at least 8. Okay. Okay. So part 1. So he's going to miss, he's going to miss, he's going to miss, he's going to miss. Okay, if he misses each of his first 4 shots. Okay, so we end up with a 5th, by a 5th, by a 5th, by a 5th. Okay, he misses, and he misses, and he misses, and he misses, which is a 5th to the power of 4, which is something very small. 1 over 625, which is 0.0016. Okay, or we could use Bernoulli Trials. Out of the 4 shots, so I'm going to take scoring as a success and missing as a failure. Okay, so success is score, failure is miss. So out of the 4 shots, I would like him to have no successes. The probability of success is 4 over 5. He's to have scored none of them. The probability of failure is 1 over 5, and he's to miss all 4. Okay, when you put it into the calculator, you'll find that 4 choose 0 gives you back the number 1. Anything to the power of 0 is the number of 1. So you end up getting a 5th to the power of 4, which is exactly what we had up the top. Okay, so that's how the top way of doing it and the bottom way of doing it links to each other. Okay, so again, just to reiterate, I've chosen success to be scoring and failure to be missing. So 4, I'd like to score none. So 4 choose 0. 4 over 5 to the power of 0, that's to score. And this is to miss. Okay, and of course the same thing would be to go my success to be a miss and my failure to be a score. And your brain may think this way because the question asked you to miss all 4 shots. So therefore, if your success is a miss, then out of the 4 shots, you'd like to miss all 4. So the probability of success or the probability of missing is a 5th. And you'd like to miss all 4. The probability of scoring is 4/5, and you'd like to get none of them. Okay, so just like before, you'll find that 4 choose 4 is actually 1. This is a 5th to the power of 4, and 4, anything to the power of 0 is a 1. Okay, and that's how this ends up being the exact same thing as well. Okay, so whichever way you prefer, you can do part 1. He scores exactly 3 out of his first 4 shots. Okay, So again, I'm going to go with success being score and failure being a miss, because that just intuitively makes more sense to me, that a success is you score your goal. Okay, but he scores exactly 3. So out of the 4 shots, which is here, I want him to score 3. The probability of scoring is 4 out of 5, and I want 3 scores, so therefore I'm left with 1 miss. Okay, because if he's going to score exactly 3 out of his first 4 shots, then he's obviously missed one of them, because something has to happen all 4 shots. So if I put that into the calculator, so 4 choose 3 by 4/5 to the power of 3 by a 5th is 256 over 625, or 0.4096. Okay, and then how would you do that? By the very first method I used in part 1. Well, if he's going to score exactly 3, then we're going to have score, 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 miss, score, score, miss, score, score, miss, score, score, miss, score, score, score. So each of these is going to be a 4 of a 5th, 4 over 5, 4 over 5 by a 5th, and I have 4 of them, all in different orders. So 4 choose 3, if you put that into your calculator, you will get the number 4 for that, for 4 choose 3, and that makes sense because I've 1, 2, 3, 4 different ways of doing it. So that's what 4 choose 3 does. It tells you how many combinations you have of achieving whatever the question asks for. In this case, scoring exactly 3 out of the first 4 shots. Okay, and you'll see in each of these lines you have 3 scores. Okay, I'll just highlight 2 options. So in each of the lines, albeit in a different order, you have 3 4/5. Now remember, the order in multiplication doesn't matter, so that is the exact same as if I wrote 4/5 down here by a 5th by 4/5 by 4/5, which is this option. Okay, so in all of them you get 4 times 4/5 to the power of 3, 1, 2, 3, by a 5th to the power of 1. So that is all Bernoulli Trials is. It's just a really nice, neat way of doing, of working out the probability of an event. Okay, so now to do part 3, I'm just actually going to delete out where I showed you the long way. It's on the recording anyway, so do feel free to go back to see it. I'm just going to delete out this bit to give me a little bit of room to do part 3. Okay, so that's part 2, and this is part 3. Okay, so he takes 10 shots and he scores at least 8. So at least 8 is he scores 1. No, he scores at least 8. So he scores 8, he scores 9, or he scores 10 of the shots. That's what at least 8 means. Okay, so you just, when you see the words exactly, it's fine. It's just one option for it. In this case, 4 choose 3. But when you see at least or at most, you have to be a little bit careful because there's more than one answer normally. When you do a Bernoulli trial and in choose or, you can only ever in one sum work out exactly or times. Okay, so in this case, in part 2, I was working out exactly 3 successes. Okay, so when I have a question like part 3, which is very, very common on a Leaving Cert paper, at least 8 of them, think for a moment, what does at least 8 means? And you can see I started to write down 1, 2, 3, 4, 5, 6, 7, 8, but that was answering at most 8. Okay, just think for a second, what is at least 8? So in this case it's 8, 9 or 10, and then you work out exactly 8. You then work out exactly 9, and you work out exactly 10. Okay, and then or, you should know from the last recording, means you add the probabilities together. Okay, so let's do that. So exactly 8. So we were having 10 shots. So out of the 10, I want to score 8 of them. The probability of scoring is 4/5, and I want to score 8 of them. So therefore, for the last 2, I must be missing them. So 10, choose 8. I'm just on my calculator now, just working it out. 4/5 to the power of 8 by 1/5 to the power of 2. And I get 0.30199. Okay, there's my 10 shots accounted for. 8 I scored, 2 I missed. You always have to account for all 10 shots. Okay, so out of these 9 shots, out of the 10 shots, now I want to score 9 of them. The probability of scoring is 4/5, so I need to score 9 of them. So therefore I must miss the last one. So it's 1/5 to the power of 5. Let me just change that in my calculator. So 10, choose 9, 4/5 to the power of 9 by a 5th, and I'm getting 0.2684. Score exactly 10, if I could spell, is 10, choose 10. So out of the 10 shots, I want to score all 10. So I have 4/5 to the power of 10, and I want to miss none of them. Okay, so 10, choose 10 is 1, 1/5 to the power of 0 is 1, so really it's just 4/5 to the power of 10 in this case. And I'm getting 0.1074 for that. Add all of them together, and I would expect a fairly high number here. And I'm getting 0.6778. Okay, why do I expect a fairly high number? Because you have an 80% chance of scoring. So therefore to score 8, 9 or 10 out of 10 is fairly likely. Okay, so that's at least 8, 9 or 10. Very common leave and cert question. Okay, check our answers. Oh, they've left them in decimal, but anyway, not to worry. That okay? So again, there's loads there for you to try. I'd like you to try question 7 over here, and let me know how you get on. Like I always said, if you need more practice, please do them and send them to me. I don't mind at all. 11 looks like a decent one as well. Okay, so 7 and 11. Okay, so that's Bernoulli trial, extremely important. Okay, called Bernoulli trial, most commonly in leave and cert books. Its official name is the binomial distribution. Okay. So now I want to bring you on to the normal distribution and probability. The normal distribution curve, here in the book, often called the bell curve, is one of the most important curves that we have in anything. Anything that you need to do statistical analysis on, the bell curve is super important. Okay, what you find is that if you take enough data on a lot of things in this world, the data or the outcomes from your experiments will approximate a bell curve. Okay, so what do I mean by that? Okay, I'm just going to draw for a few minutes to explain the bell curve. So the bell curve, completely symmetrical. Down the middle of it is your mean. Often given the Greek letter mu. Okay, bell curve may look new to you, but it's not overly new. You would have previously represented data that followed a bell curve in a histogram as such. Okay, so you can see, if I could draw, that the normal distribution curve just fits over it. Okay, remember what your histogram was. This was frequency on the y-axis, so the most frequent value is that one in the middle. Okay, so you're not too surprised then to see on the normal distribution curve that the mean is the value in the middle. Okay, it's the most frequent value. Okay, when it's completely symmetrical, and I haven't got to stats with you yet, but for anybody who has done stats or knows a little bit about it, in a completely symmetrical curve, this will also be the mode and it will also be the median. Okay, the three measures of center will lie completely on top of each other. Okay, let's go back to the book for a minute. One reason the normal distribution is so important is that the measurement of many natural phenomena are normally distributed or nearly so, such as heights of people, such as weights, such as IQ scores, such as exam results. So what does that mean? That means if you gather enough data about any of these natural phenomena, they will fall under a normal distribution curve. So think about shoe sizes. The most common shoe size for a lady is probably size 5 or 6. It lies there in the middle. Then you have size, we'd say 6, 7 and 8 up here, 4, 3 this side. Okay, so 5, 6 lies in the middle. For men, it'll be something similar. Maybe size 8 is here in the middle, so you have 9, 10 and 11, 7, 6 and 5, or so on and so forth. And they don't have to be full shoe sizes. It's a statistical analysis. Okay, so that's what it means by it's normally distributed. Okay, if you think about exam results, so in many cases in maths, the most common maths results is a H3 or H4. Okay, so your H2s then are here, or H3 is somewhere here, H2 and H1, and then in the same way your H4, H5, H6. Okay, so that's why things like exam results are said to fall under a bell curve or fit a bell curve. Many people say that it's forced to fit a bell curve. It's not forced. It naturally fits a bell curve. Okay. Now, what's even more special about the bell curve, though, is that we can use what's called an empirical rule from it, or we can read an empirical rule from it. Okay, so the empirical rule is all about the mean and what's called standard deviations. Standard deviation is one of the measures of spread in statistics. When we talk about the normal distribution curve, we literally take the curve and we chop it up into 6 sections of equal width, where each of the widths is a standard deviation. So I have 3 standard deviations above the mean, and I have 3 standard deviations below the mean. Now, what's really nice about the normal distribution curve is that if I go down 1 standard deviation and up 1 standard deviation, I will find that 68% of the total area of that curve lies between this point and this point. Well, what does that mean? Well, if I go back to exam results, I can then say with certainty that 68% of Irish students will get between a H3 and a H4 in all of their exams. I can say for men, now assuming I have the data right, I can say 68% of all men have shoe size between 7 and 9. and so on and so forth. So anything that fits under a normal distribution curve, you can say with certainty that 68% of people will lie between here and here. So remember your histogram, your frequency, okay, it was how often it occurred, 68% is between these 2 points. I can then say, so point 2 of the empirical rule, 95% of the total population is between this point and this point. In other words, up 2 standard deviations, down 2 standard deviations. And in a similar way, I can say 97.7% of the population is plus or minus 3 standard deviations. Okay, and that is extremely useful when you're doing any sorts of statistical analysis, as you will see when we get onto that chapter, that we can use this empirical rule when we need to. The other 0.3% of the population is outside of the normal distribution curve. It's here somewhere or here. So for example, exam results, they would be the people who would get 6 to 5 points, or they would be the people who bomb out completely. If it's shoe sizes, it would be people with really tiny feet or really big feet. For the heights of people, it would be the exceptionally tall people or the dwarfs. So it is the people who we say don't fit the normal distribution curve. Okay, their data is perfectly valid, it just doesn't fit under this curve that represents 99.7% of the population. So that's the empirical rule, not written anywhere. You have to know these 3 values, and you have to know the number of standard deviations that they represent. Okay, so you have to know that if you go up 1 standard deviation up, and it's a Greek letter for standard deviation, and then go down 1 standard deviation from the mean, that's 68% of the data. Okay, in a similar way, from the mean, you have to know that plus or minus 2 standard deviations represent 95% of the population or the data, or however you want to describe it. Plus or minus 3 standard deviations represents 99.7% of the population. Okay, there's a grand old delay there between me writing and it updating on your screen. And you just have to know those values. They're not written in your log tables. If there's no question in your book, which I would say there will be, but if there's not, I will find you one to show you how exactly do they ask you the empirical rule. Okay. That then leads on to what's called ZScores. Okay, so the most frequently used normal distribution is the standard normal distribution. There are other ones. There's called the Chi distribution that's used when your sample size is very small. There's a Poisson distribution that's used when you don't have means, and so on and so forth. So there's quite a few, but the one on your course is the standard normal distribution. We usually reserve the letter Z for this distribution. In particular, we learned how to change a scale from X units to Z units, and we define the standard unit as Z is equal to X minus U over theta. Okay, so we obviously haven't done that. So the Z-scores are used for, you may not have come across them, Z-scores are used for normalizing different sets of data so we can see which set of data is better than another. Okay, so how does it work? Well, it uses the empirical rule two-way, and it's what's called, it normalizes the data. Okay, so Z-scores. Okay, so it takes our normal distribution curve. Let's try that again. Okay, it gets the mean of it. Okay, so that's my mean. That's my mean mu. And then it splits it up into 3 standard deviations up and 3 standard deviations down. Okay, so what we have here is mu plus standard deviation. What we have at this one is mu plus 2 standard deviations, and what we have here is mu plus 3 standard deviations. What we have here is mu minus 1 standard deviation. This one is mu minus 2 standard deviations, and this one here is mu minus 3 standard deviations. Okay, so rather than write all that in, we tend to say mu is the value 0, up 1 standard deviation is 1, this point here is 2, and this point here is 3, this is minus 1, this is minus 2, this is minus 3. Okay, so we normalize the data, so rather than have a specific value, we ask the question, how many standard deviations are you away from the mean? Okay, let me just charge my laptop. So there's a formula for that. It is your Z-score is equal to the value compared to the mean over your standard deviations. So in other words, this is the value that I'm testing. This one here is the mean of the data, and this down here is the standard deviation. Okay, so maybe let me give you an example. So I would say you took a class test and the mean in the class test was 68% and the standard deviation was 10%. Okay, so the whole class took a test, we did some analysis of it afterwards, and it turned out the mean was 68 and the standard deviation was 10%. Okay, if you told me then that you got, for that test, you got 70% and you thought you did poorly, well, let's compare you to the class. Okay, so let's take your 70%, which is what I mean by the value that I'm testing, let's compare it to the mean over the standard deviation. Okay, so 70 minus 68 is 2 over 10, so it's 0.2. Okay, so what does that mean? Well, that means that you're 0.2 standard deviations above the mean. So now your actual value of 70 is put into context of what did the entire class get and what was the spread, which is the standard deviation between the lowest and the highest marks. Okay, so that's your Z-score value. Okay, now what does that mean? What does a z of 0.2 means? Okay, I'm going to stop sharing now so that I can get some log tables. Log tables, and there's probably loads of these online. I just know UL has a copy up here that I use quite a bit. Okay, so if you scroll down your log tables, you will come to the stats sections of it. Okay, so let me see, do I have an actual copy of log tables on my desk? No, let me just get one. So what you're looking at in an actual log tables is page 36 and 37. Okay, so what does a z-score of 0.2 means? So there's 0.20, which is 0.2. So you can see the z is here. So I look up the value. These are the whole number and the first decimal place. So if you can see, I have everything from 0 down to 3 standard deviations. And these are the second decimal place across the top. So that's why I'm going for 0.20, which is here. So 0.5793. So let me just write that down here. 0.5793. Okay, what does that mean? Okay, well, what that actually means, 0.5793, if I write that as a percentage, is that you are 57.93% of the class did worse than you. Okay, see that blue line I drew? The area of this curve, if it's normalized 100%, okay, that represents 59.93%, or roughly 60%. So 60% of the class did worse than you, about 40% of the class did better than you, and I'm just rounding to the nearest decimal. Okay, so that's what normalizing the data means. You compare it to the mean and you compare it to the standard deviation. Okay, so we normalize our scores so we can do comparisons. Now, what I'd like to do with you, because I'm conscious some may not have experience of ZScores, is I would like to do an exam question with you that shows you how do they ask these type of questions. So 2018 question 2.